So this is the video for section 1-2, and we're going to be talking about how to move from the idea of the slope of a line in section 1-1 to the slope of a curve. So we touched on a lot of this last class, but the first idea that we want to morph from a line to a curve is the idea of a tangent. So hopefully somewhere along the line in your geometry life, you discuss the difference between a secant, which would be a line segment in a circle connecting 2 points on the circle, and a tangent, which would be a line drawn that touches the circle only in one spot. So we're going to use this as a framework for what we're going to talk about in terms of a tangent. Although in a curve, the tangent line may or may not only touch in one spot. So we have to be careful about that. But the idea being the tangent line in this circle is going to be a way that we're going to express what's going on at in the circle at that particular point. If I moved from left to right along the x-axis, what would be happening along the y-axis if I had graphed this in a plane? So we're going to use that tangent line to best approximate what's going on in that circle by doing something called, or doing something we would call zooming in. So, if you have your cell phone and you're having trouble seeing something and you make the picture larger, you zoom in on it. The more you zoomed in on this particular area here, the more the circle itself would start to look like the line segment. Because the closer and closer you get in, the less distance there is between the line and the circle. And so it would start to look like a line segment, and we could then think about its slope because a line, all we need is 2 points and we could get a slope. So if you look at this example here, this isn't a circle, but it's a curve. And zooming in closer and closer to this point P that's on that function makes the function itself that we see curves here look less like it curves because we're getting closer and closer and closer to this one particular point. And if this is a place on the curve where we have a relative maximum and we zoom in closer and closer, we can see that curve starts to look more and more like a horizontal line. Or if our curve is decreasing and we zoom in and in, we can see it look more and more like a line with a negative slope. So the idea behind that is we can talk about the slope of the curve if we approximate that steepness with a line segment that goes through that same point in the same motion that the curve does. So for example, if somebody drew this function for me here, P, and I was taking a look at it and I wanted to know right here on this curve, what does this function look like it's doing? If I tried to move to the right 1 unit, how much higher am I going to be? That's the idea of slope. And you can see that if you did that, you would have a little difference in the actual value of the function versus the value that you would be using as a tangent line to the curve. There's a little bit of difference there, but we, depending on how big a deal it is that we're off a little bit, maybe using that tangent line would be a good approximation for the steepness of the curve there. And if we use that tangent line, we can see that it has a slope of 1. So we could estimate the slope of the curve there with that same number 1. Now we'd be off because our steepness it's not quite as steep as that line segment. But if we tried to go beyond that and estimate, if we tried to take 2 steps to the right, then we'd be off a lot more. So anytime we use this idea, we're talking about very, very close to that point. What is the curve doing in terms of its motion? How much is it going to rise if I run? So we're thinking about slope in that sense as a rate of change. The slope at point P measures the rate of change of the curve as it passes through that point. So in a really close neighborhood around it, we can say its rise and run is about 1 to 1. So if you're looking at your curve, a curve that has more turns, twists and turns to it, using that same logic, we could notice here that if I'm at the point 0, 1 on this function, it looks like I'm at a point on that curve where if I'm looking left to right, the curve was increasing and now it's decreasing. So at that particular point on the curve, it's like an in-between. It's in between a positive slope and a negative slope. And so the tangent line at that point would look like this. It would be drawn as a line that has a horizontal slope, neither negative nor positive, but the transition between the two. So when x equals 0, we would say the steepness is 0 because it's a horizontal tangent line. Whereas when x equals 2, we look at this tangent line that was drawn and use it to estimate the steepness of this curve. And this tangent line has a steepness of 4. So the steepness of the curve here is 4. The steepness of the curve here is 0. Here's another place where the steepness of the curve would be 0. And then in here somewhere between these, the steepness of the curve would be negative. Now, negative what? We'd have to do a little more investigation to figure it out. But here they nicely gave us the tangent line so we could just use their slope. So how are we going to figure out these slopes? I mean, positive versus negative is pretty easy to see, but how positive or how negative is not quite as easy. So let's just first look at the curve y equals x squared. I've got a picture here that I pulled from the book, but I want to sort of do a dynamic idea of what they're doing here with y equals x squared. So if I want to know the steepness of this curve right here, nobody's drawn a tangent line for me. I can't measure a slope because I don't have the line. But one way we could get toward being able to figure out the steepness of that tangent line would be to draw a secant line that hits the curve at 1, 1 and 2, 4. So if I drew that secant line between those 2 points, it's not a tangent line, but it's not too far from what a tangent line would look like that would touch that curve at one point. And I could figure out the slope of that line and use it as an estimate for the slope of the tangent line. So in this case, my slope would be 4 minus 2, or I'm sorry, 4 minus 1, because y2 minus y1 over 2 minus 1. So the slope of that line segment is 2. But, excuse me, I saw the point 4, 1, 4, oh my goodness, I'm thinking backwards here, sorry. 2, 4, 0.24, and the 0.11, and I subtracted wrong. So that's 3 over 1. That slope is 3. 4 minus 1 over 2 minus 1. That slope is 3. Rise 3, run 1. Would have been easier to say. But what if I want a better approximation of the tangent? Then I could pick a point here on the curve, and that is the point where x is 1.5, so I'm midway between. And if I square 1.5, the y value is 2.25. And I could draw that secant line. That's actually going to be a better approximation of the tangent line, because you can see as I drew it, it's closer to what the curve is doing there. It's a little hard to even see. My pencil's pretty thick, but the difference between the curve and the line there, because I've zoomed in. And the slope there would be 2.25, the y value. minus 1 over 1.5 minus 1. And that is 2.5. So that's a little better approximation what the tangent line slope would be. And I could keep doing that. I could keep pulling myself closer and drawing that line that's a better approximation. And that's what this picture is doing. They're calculating a slope if they use this as their second point. And then a slope with this as the second point. And then it got a little closer, and even a little, can even get a little closer with 1.21. And what they're finding is if they kept doing that and splitting the difference and splitting the difference, they could figure out that the slope of the tangent line right there is 2. And if you've had calculus before, you would already know that, but we'll talk about why it is. But for now, in this section, it turns out that it will always be the case that if you're talking about this particular function, y equals x squared, and you want to know the slope of the tangent line anywhere on that curve, all you have to do is double the x value of the point. If you double the x value of the point, you'll know the slope of that curve at that point. So in other words, here at the point 0, 0, the slope of the tangent is 2 times 0, which is 0. It's a horizontal tangent line. Over here, if I have a x value of negative 3, the slope of the tangent is negative 3. Times 2. So it's negative 6. Writing and talking at the same time. So I'm plugging in an x value of negative 3, and the slope is negative 6. I double the x value. And this is going to be a rule that you're going to need to do any in the math lab. They're going to assume that you know for x squared and only for x squared, the rule to get the tangent slope is double the x value. One other idea, I want to show you what you can do with your graphing calculator. Just, if you have one, you can play around with it a little bit. Your graphing calculator can help you do that zoom idea, to zoom in on the function. Because if you put your function in your calculator and you graph it, sorry, I've done this before, so I'm ruining the surprise. So let's get my window better. Negative 10 to 10. Negative 5. 5. That's not going to be a good one. I'll do that. Okay. So I'm going to graph my function. I did not mean to do that. Okay, so let's try that again. Negative 10 to 10. Negative 5 to 5. Okay. So there's my exponential function. You can see that it's, let's see if I can get a better picture of it. Okay, so you can see that it's exponentially growing here and shrinking towards 0 on that side. That's what 3 to the x does. So if I want to zoom in on it, I can hit zoom. Sorry, I'm trying to hold it and look at it at the same time. There we go, zoom. And we can zoom in, but we got to get the point we want to zoom in on at. So I'm going to put it back down so I can do this right. So I'm going to zoom, and I'm going to zoom z decimal. And then I'm going to find a point on the graph like 0, 1. So I'm going to trace it, get that point 0, 1, and I'm going to zoom in. And it's going to zoom in around that point 0, 1 when I hit enter. So it's getting closer to that point 0, 1 when I do that. Now I'm going to zoom in again. And I want to say still keep that point 0, 1. And the closer and closer I get, the more this thing looks like a line. So I could zoom in until I really feel like it does look exactly like a line. And I won't be able to really tell the difference between them. That's still the curve, but it looks like a line because I'm so close. Then all I would have to do is trace, move a little to the right, and there's another point on the line. And I can use that point, and it's not a line, it's a curve, it just looks like a line. That's another point on the curve, and I can use that point to figure out the slope of that tangent line and get pretty close to the right answer because these 2 points are pretty close to each other. So if I did that, I could subtract my y values, subtract my x values, and get a slope of the curve approximately by using my graphing calculator. So it's doing the zooming in for me, and it's getting these points that are closer and closer so that I can do a calculation. Okay, so that's the end of section 1-2. I'd like you to try the homework, make sure you come ready to move on to the next section. But if you have any questions, we can definitely go over them when we meet again.